Welcome everybody to session 5. This is going to be a continuation of the discussion in the previous discussion, but in the previous session, but also some new ideas in regards to not only making science accessible for all students, but specifically using using phenomenon to and student inquiry to drive that instruction. My name is Andre De Leon. I'm the K-12 science education programs professional for the Nevada Department of Education in the state of Nevada. I am going to not only introduce our presenters, Erica Palis and Matt Crable, but also our facilitator, Robert Ma, who is going to take over for me as I step out of this virtual room. Go ahead, Erica and Matt, and we'll go ahead and get started.
Great. Welcome, everyone. Thank you, Andre. Like Andre mentioned, my name is Erica Palis. I'm joined by Matt Crable. If you're in the last session, you got to hear from Matt quite a bit. I'm a project manager for OpenSciEd. Before this role, I was a teacher in the classroom and I used OpenSciEd in my classroom. So we're excited to speak with you today about using phenomena and student questions to drive science instruction. And we'll spend quite a bit of time looking at the instructional model within OpenSciEd, the different routines, and hopefully it'll get you interested in taking a look at our materials, but you'll hopefully also get some ideas that you can apply into your classroom without using our materials as well. So Matt's going to drop the slides in the chat. You can access those now if you like to have those open. Otherwise, you can access them later. It will be available for you. Just a little bit about OpenSciEd, the really quick elevator pitch version. OpenSciEd is a nonprofit organization. We're kind of made up of 4 categories. So the first are our developers that actually create and write the curriculum. Then state science administrators. So we have 10 partner states. And through those 10 partner states, we have a committee that provides guidance and is like an advisory team over all of the work in developing our curricular materials. Within those 10 states are also where we field test the materials prior to their release. So teachers are using these materials in their classrooms and then providing feedback. And then that feedback is used to revise before we release those units publicly. So teachers are really essential to the creation of these units. And then, of course, funding. We need funding to make this work happen. And so we are generously funded by multiple philanthropic organizations. And the result of that is free materials, free high quality, full course curricular materials that are NGSS aligned, as well as outstanding professional learning experiences to help prepare teachers to use those materials. So just some background, our middle school curriculum is complete and available for download on our website. We are beginning to release high school units starting this February. So the first units for chemistry, bio, and physics will be released in February. And then elementary school science, it has just started development. Today in this session, we're going to look at some examples from 2 different units. So they're outlined there on this scope and sequence, just so you have a general idea of where they fall in the intended order of the units. So we'll see some examples from those 2 units today. Quick snapshot. So we're going to be focusing on this idea of coherence from the student's perspective and how phenomena and student questions are used to drive that and make learning coherent for our kids. We'll dig into the different routines that support coherence. And then if we have time at the end, we'll have a Q&A, but well, we got a lot to pack in, so we'll see how much time we have. But I encourage you to drop questions in the chat throughout the next 45 minutes. Any questions you have, put them in the chat at any time. Matt will be able to answer those and monitor that, even if I'm unable to. So please drop those questions in the chat if you ever have one. We're going to be using a Jamboard today. So we'll drop that link into the chat. We'll all be on the same Jamboard. If you have difficulties using Jamboard at any time, or if you just would prefer not to have another window open, you can always just add your comments in the chat as well. but there will be one interactive activity, 2 interactive activities that are made easier on Jamboard. So I invite you to have that open somewhere on your screen. Quick overview of Jamboard, at least the features we'll be using. We'll be adding stickies primarily to the Jamboard. So you'll click that little icon and then this sticky note box will pop up and then it'll add your idea onto the page. You can page through different tabs, kind of like slides at that top section as we move through our session together. Okay. All right, so let's get into this idea of coherence from the student perspective and what that actually means. So I want you to think about this question on the screen, probably a question that has been asked in your classroom before. If someone entered your classroom and asked a student, what are you doing and why? So someone enters and talks to one of your students, what are you doing and why? How might your students respond? And how would you like them to respond? Just taking like 20 seconds to independently reflect on that. Personally, you don't need to share your response anywhere. And so this is a key part of when we think about coherence from the student's perspective. And the kind of problem of practice we're going to be focusing on today is that students often experience science class and any class as a series of disconnected activities that lack coherence or connection both between and within lessons, right? So our goal, right, is that from one day to the next, from one lesson to the next, it's telling the story that students understand, but often things can be disjointed from their perspective. As teachers, we know the progression of learning. It makes sense to us that this is the best way to do it or a good way to do it, but students don't always see the connections between and within lessons that we would as an educator. So we want to organize and enact curriculum that is coherent for them. So we want it to be designed to help children continually build on and revise their knowledge, start from their curiosity. We want students to be able to make sense in their own voice, right? Be authentic in their learning. And so instruction that's coherent for students looks like some of these things, has some of these features. It's applicable to students' lives. It's driven by their questions. The students are figuring out science ideas instead of just learning about them. Students are discussing in their own voice, and they can describe the story of their learning, right? Getting back to that reflection question, students can describe the story of their learning. They know what they're doing next and why, and they feel ownership. And so these green boxes, this is kind of our foundational goals to make coherent instruction happen. We want to start with student questions. We want to build on their prior knowledge, and we want to continuously be making connections. Okay, so the approach within OpenSciEd, how do we do this? How do we support students as partners in this work? There are 4 key questions we think about. How do we kick off a unit? How do we work with students to motivate the next steps? How do we help students use practices to build science ideas? How do we help students put science ideas together? And how do we push students to go deeper? And the response to these 5 key questions are these different routines that make up the OpenSciEd instructional model. So we're going to move through each of these routines and give some examples of them. Throughout an OpenSciEd unit, every unit starts with this anchoring phenomenon routine. And then the other 4 routines are sort of woven throughout. So like I mentioned at the beginning, we're going to see some examples from these 2 units. So 6.4, plate tectonics and rock cycling, and then 7.3, metabolic reactions. We're going to look at some examples of those 5 routines using these 2 units as context. So let's start. Let's do some science. So the anchoring phenomenon routine, like I mentioned, every unit, all 18 units start with an anchoring phenomenon. And this is how we kick off the investigations. And the purpose is we want to be developing curiosity, that's going to drive the whole course of the unit. So the anchoring phenomenon anchors the rest of the learning that we do throughout the unit. There are 4 parts. We're going to move through these 4 different elements of the routine together in an example. And our first step is to explore the phenomena. Okay. So we're going to put our 6th grader hat on in a minute, and we're going to watch a video of a puzzling occurrence that has happened. And while you're watching, I want you to jot down some things you notice and questions you have while watching the video. So in the chat, you can type them and then hit enter when you're done. You could type them as you go and send them into the chat, but you're going to share your noticings, the things you observe, and then your questions that you have while watching. Okay. Uh-oh, I can't make you bigger. Improvising. Okay.
On Everest, Jim Davidson and his friend Bart are resting in their tent.
All of a sudden, we heard a rumbling. Instead of fading away, it started getting louder and it started getting sharper. When I heard that noise, I knew that we were in some sort of special bad situation. I looked at Bart and I said, "This is really bad."
I feel this tremble underneath. And the tent shifts on the ice. I hear like a big crack underneath the ice, as if the ice is splitting underneath our tent. The reaction was like, let's get out, right now.
Some interesting things going on with these climbers. Can we drop some things you noticed or some things the climbers noticed in the chat, or questions you have as a student? Questions you think your students would have? Great question. What's causing the rumbling sound? Yeah, like that seems scary. Do they survive? What exactly is going on? What is cracking? Yeah, what? Great questions. Yeah, there was a part where the footage was like shaking. The tent was moving. Why is that going on? Oh, that's a good one. Yeah, it seems like, or yeah, it seems like they maybe should have some better priorities than getting their cameras out. Ooh, is the Earth moving above or below? Lenina, I'm curious what you mean by that. Moving above or below? Great questions. All right, we're gonna learn some more about this strange phenomenon that we see happening in this video. We're gonna look at a reading. Okay, we're gonna look at a reading that talks about what's happening at Mount Everest and what happened that day of that video. Okay, so we're gonna drop this reading in the chat. And same thing, I'm gonna give you a couple minutes to read through it. And then as you're reading, think about the same thing. What are your noticings and wonderings? Go ahead and type them in the chat, but don't hit enter yet. I'll have you guys hit enter after we've had a few minutes to read it so we can all add our ideas at the same time. But reading through that, what do you notice and wonder? Type it in the chat, and then we'll all click enter together. Give us a few minutes to read. So as you're reading, you're looking for noticings and wonderings. What stands out to you? What questions do you have? Type them in the chat and then we'll hit enter in about 1 more minute or so. All right, if you're ready, go ahead and click enter and send your ideas into the chat. Noticing things that stood out or questions you have or some of both. Oh. How is the mountain moving northeast? Yeah, it's talking about the mountain like moving in a specific direction. They talked about it getting taller. The reading talks about earthquakes, what's causing them. Great questions. I like Aurora's question. Unsure why anyone would keep climbing Mount Everest with so many deaths. Yeah. Ooh, the most accurate data was when both countries were working together. Oh, why is the earthquake making it rise instead of sink? So lots of interesting questions, lots of things jumping out to us from that article and from that video. We're going to watch a classroom. Oh my goodness. Talking about their noticing and wonderings. So they just experienced the same thing. They watched the video. They did some other activities too that we skipped over. And now they're looking at the reading and they're discussing as a group what they noticed and what they wonder.
What did you guys notice? I found that it shrank 2 feet in that it shrank 2 feet in 1934.
No, it says here. However, the data show that the earthquake moved the mountain. Wait, does it say that
it moved 2 feet?
Oh yeah.
In 1969.
Well, it didn't change height, but it did move directly.
Well, like it shrunk by 63 centimeters. And that's kind of a lot.
After gathering data from sensors, scientists determined that Mount Everest did not change height due to the massive 7.8 magnitude earthquake and will continue to grow at its normal rate.
Yes, but it also says in the last major earthquake near Mount Everest in 1934, the mountain shrunk by 63 centimeters, which is almost 2 feet. So that's what I wrote down in my note.
Oh, well, it did shrink 2 feet, but it wasn't caused by the earthquake.
In the last major earthquake near Mount Everest, shrunk though.
They're saying scientists were curious if the earthquake had caused this. Then later they said because when they collected data, they said it did not change height due to the massive 7.8 magnitude earthquake.
Yes, but I'm just gonna write. I'm writing in the notice because I noticed that in 1934 it shrunk.
Oh yeah, so you're gonna see like why it shrunk?
Yeah.
Okay, so noticing some similar things to what we called out, having a discussion, breaking down that article in small groups. The next step of the anchoring phenomenon routine, we have our elements kind of tracking us at the bottom. So that was just exploring the phenomenon, experiencing it. We have this shared experience as a class. And now students attempt to make sense. And in this particular lesson, they do that in the form of an initial model that we're going to see a clip of. And so they've got a lot of questions, some observations, and now they're documenting their current ideas, right? We haven't figured anything out, so they're documenting their current ideas, and we'll see another video clip of this happening in the same classroom.
So in your model, I want you to show how Mount Everest is actually getting taller by 6 to 7 centimeters each year, okay? And at the same time, I also want you to think about how is it actually moving to the northeast. So not only is it growing taller, right, but it's growing taller and it's moving. So I want you to think about what is actually causing that change. That timer's up there. I want you to work under that time constraint. Does not have to be fancy, simple ideas. How is it actually getting taller? How is it moving to the northeast? Okay, can you share out not what they said was puzzling, but can you share out what your partner said was puzzling about their model? As a way to show that we were absolutely listening to our partners. Rodney, go ahead.
That the tectonic plates make it grow bigger.
What do you mean the tectonic plates?
So how they shift and then points it up and then the mountain grows.
So I heard you say it was puzzling, and who did you speak with?
Miles.
Okay, so it was puzzling about tectonic plates making something bigger. Is that what I heard you say? Great, thanks for sharing about Miles' work. Sophie.
So this was kind of, I had two partners, so
Great.
Both of them said this. Kind of confusing how the tectonic plates actually worked and like what happened with the tectonic plates.
Okay, yeah, and to be honest with you too, that was a fancy word that I've heard some people saying and looking at people's initial models, not everybody had that, so maybe that's something we have to figure out about too. Great, thanks for sharing, Toby. Toby, what'd your partner say?
I had two partners, and Ethan said, thought that the snow came down and then it would push the mountain up because it would all catch at the bottom.
Okay.
Okay, so students had some time to document their own ideas, then they discussed with a partner, and then we see them sharing as a whole group. And out of this discussion, sort of what happens next is they build what's called a consensus model, an initial consensus model. So as all the students are sharing their different ideas, they're then creating this class representation of what they think at this moment, at the very beginning, what types of things do multiple people have? What types of things do we have questions about? Right, so this is giving us our starting point, right? Our starting point. This is where what we currently are thinking, whether it's scientifically accurate or not. This is our current ideas. The next step, element 3 down here, identify related phenomena. So students start to think about some things that maybe are similar to what they saw in the video, similar to earthquakes, similar to mountains growing or the land changing, like this prompt here. Where else in the world does the land seem to change slowly or suddenly? So students think through some things that could be connected. Here's an example from that same class we've been seeing of some of the ideas that those students came up with. And then element 4, this last step is to generate questions. Okay, so students create a driving question board. So Matt's going to drop the Jamboard link in the chat again in case you closed it. But on our Jamboard, we have a little driving question board. And so we're going to add some sticky notes with some of our questions that we have about this phenomena. Okay, so we're on the very first frame there. Ooh, okay, I'm seeing some questions about OpenSciEd. So I'm actually going to move these to another one because that's great. Okay, can I copy and paste this? Okay, so just to be clear, I'm going to move these ones. This is awesome. You can totally put other questions you have on here if you'd like. But on this green one, we're going to put some questions that as a student, thinking like a student, you would have about that phenomena we just experienced. So we did have some of them in the chat. It could be some of those same ones that you were thinking previously. But grab a sticky and throw a question on this driving question board. Awesome, we've got some being added. Oh yeah, this one popped up in the chat too. Do mountains ever get smaller instead of larger? You have a similar question to one someone's posted, still add it, right? That's awesome. If we have similar ones, then we know that that's an area or a topic that we really want to investigate. Oh, I like that one. That yellow one that just popped up. Ooh, volcanoes. That's maybe a related phenomena too. What's the connection between Everest, between volcanoes? Okay. So students would be adding questions to their class driving, their class's driving question board. Maybe it's a digital format, maybe it's a poster on the wall, a bulletin board. There's lots of different ideas that teachers use. We're going to look at some other some examples from students in a minute, but they are in the Jamboard on some of the later slides. You can see some questions that I pulled off primarily Twitter of driving question boards for this unit that teachers had shared. So you'll see some examples of actual student questions on those later frames, but we'll look at those together in a little bit. But here, these are some of the ones that students came up with in real classrooms, right? Do all mountains move? Could snow or an avalanches change the height? Lots of students have questions about the snow and ice sometimes. Can Chicago have earthquakes? Why or why not? Thinking about different locations and if the same phenomenon could happen there. So after we've generated questions, we would think about where do we need to go next? What do we do with all of these questions? How do we start to answer them, right? And so students would work in maybe small groups, a variety of different ways that this element is done, but they would come up with investigation ideas. What could we look at? Maybe it's a data source, maybe it's a simulation, maybe it's creating a 3D model and trying things out. But that's that last portion of element 4. What do we do next, right? And now we have a plan. If we begin to document some ideas for investigations, now the class has a plan and a mission to start to answer some of their questions. So in summary, right, that's the anchoring phenomenon routine. A lot of parts to this one routine, these 4 different elements. So we explored the phenomenon. We tried to make sense of it with our initial ideas and our initial models. We identified some related phenomena. And then we came up with our questions and our ideas for next steps. Okay. So in the chat, I'd like for us to reflect on this question. I don't know if you guys can hear my daughter screaming. I apologize. She just woke up from her nap. So in the chat, how does the anchoring phenomenon routine, so those 4 elements we just moved for, how does that kind of coincide, what you experienced, what we saw in the videos, with these different attributes to coherent instruction? So how does the anchoring phenomenon routine support instruction that's coherent for students? So it could be kind of connecting to some of these bullets, but I'll give you a minute to sort of read through this again. And what did we experience that connects to some of these attributes? Great, Amy put an idea in there for us. I invite others to add some ideas too. So thinking about curiosity. Previous knowledge, that connecting to their prior ideas. Allows their thinking to evolve as they gain new knowledge. Ooh, that's a great segue. So now we have all of these questions, all of these different ideas that we've generated from the driving question board and through that anchoring phenomenon routine. And now it's, what do we do with that, right? What do we do next? So how do we use those questions that we've developed from the phenomena and use them to drive the rest of our instruction, right? How do we start to figure things out and make sense of the science? And so moving into the second and third questions, we're going to be looking at the navigation and investigation routines within an OpenSciEd unit. So we're trying to answer these 2 questions through these routines. How do we work with students to motivate the next steps? Okay, how are we working with them to help decide where we go next? Instead of us knowing as teachers just the scope of the unit and we're making the decision as to what we're going to learn next, we're using students, we're doing that with students. 3, how do we help students use practices to build the science ideas? Okay, so 2 routines, navigation and investigation, are what we're going to see some examples of. So the navigation routine, it happens in between, like within lessons, like maybe a lesson is 2 days long. So it could happen from one day, from the end of day 1 into day 2, or the end of a lesson and kind of connecting us to the upcoming lesson. So it's this idea of looking back to move forward. What did we previously do? And how is that going to help direct where we go next? What did we do previously and what do we need to do now? And so the examples we're going to see for these 2 routines come from the metabolic reactions unit. So we're kind of jumping in midway through the unit. So to give some context, in the previous lessons, the anchoring phenomenon for this unit is McKenna. We're introduced to McKenna. She's experiencing various digestive symptoms. So she's sick. We analyze like a doctor's note, some of the these different symptoms that she's having and some data from that. And we're curious about what's going on. So we will go through that whole anchoring phenomenon routine, but with this idea of McKenna, we want to know why McKenna is sick so that we can help her. So we're multiple lessons in, we've started to investigate about our food and what happens when we're consuming food. And so far we figured out that burning food is a chemical reaction and it results in new products. Okay. We figured that out so far. We also figured out that fuel and oxygen react when they burn to release energy, carbon dioxide and water vapor. So we know that burning food is a chemical reaction. We also know what happens when fuel and oxygen react. So we have these different ideas about burning. And we want to figure out how they're connected. So the navigation, or getting into this lesson, we're going to see a clip from. So we're picking up from there and moving into this next lesson. And in this video, students are discussing these 2 questions as the navigation routine. What did we figure out last class? So looking back, what questions did this raise for us? Okay.
questions?
I'm gonna try and make that big again. Okay.
What questions does this raise? Remember, the big picture is about McKenna, trying to figure out what's going on. How do the fuels relate to our body? Well, isn't it clear? We put the vegetable oil and we lit it, right? So don't you have little fires going on inside of you that are producing the energy? It's not fires, but it's something similar. Oh, Camilla's gonna argue. I don't know. Do we? How did we get the combustion reaction to get going with the vegetable oil? What did we have to do? On fire, right? In order to release the energy. So if that's how we're getting our energy, you're saying we want to see, how does this happen in our bodies? I don't know. We lit it on fire. Do we have to light us on fire? There were fires inside? Then we would die. To me, that makes sense that we would die. Camilla, what do you think? So this is a great question. Did everyone hear that? No. Please remember our norm. So it means you need to speak louder, but also if you can't hear, please say that you can't hear. Don't depend on me. Come on. Say that again a little louder, because that was awesome.
So when you exercise, like what if you're burning calories like the same way that the vegetable oil was burning when
We're burning calories, right? To get the energy. And isn't that the same as burning the vegetable oil with the wick? Yarian has a little problem with that because he doesn't think we can have little fires inside of us. We can? We do get hot. So would we say that this is a question we have? We have to figure out, how is this going on inside of us?
Like once it gets like absorbed or like broken down, like what's happening to it exactly?
Oh, I saw that point too. I agree with what you said, but I think another one would be like a carbon dioxide sensor, because normally when you burn something, carbon dioxide is released. So if we were to have a fire in us, we could sense the carbon dioxide.
Oh yeah. So basically, I want to see what happens while all that stuff happens. I think there's some like acids that do something that could like be kind of like fire, but I'm not sure. So do you think that there's a fire in ourselves, or do you think that it's something similar?
in different ways? Like water is.
I honestly think it's something similar. Like maybe really similar, like acid.
Carbon dioxide is really breathe.
I don't know.
That's actually what talking about. If we breathe out,
I got it.
maybe the oxygen that we breathe in, it can go to our stomach and actually light the fire, and then we breathe out the carbon dioxide.
Oh, that's true.
Yeah, so, Mr. Clinchow, I kind of thought of something. So, two things. So, maybe, don't you have a sensor that can measure carbon dioxide?
I do.
Yeah, so I was thinking maybe you can measure, like, not that we can do it, but maybe you can measure, like, the carbon dioxide inside of the body, because normally when you burn something, carbon dioxide is released. And the second thing I thought is that whenever you...
So how does... If we can detect, prove, or collect data that there is carbon dioxide being produced in our bodies, how does that help us to say that this reaction is going on?
Well, I was just answering the question about if there was a fire in a body, that's why.
So the question of, is this reaction going on in the body, right? How does, if your idea, which I think is a great idea, to detect, if we can detect that there's there's carbon dioxide being produced in the body, how does that data help us to prove that this chemical reaction is occurring in the body?
Because if there's carbon dioxide in water, that means that that's a product of oxygen in our food.
Do you agree with that? Was that what you were thinking?
Because you like inhale oxygen, and maybe some of that oxygen could be going to where the food is.
So you need the carbon dioxide. The carbon dioxide has to be produced, right?
Yes.
So if you show that carbon dioxide is being produced, that helps to support it, right?
Yes.
But if you show that no carbon dioxide, then you know that this reaction can't be happening, right? Good.
So maybe you can like.
Okay. All right, so students have been discussing what they did previously and now grappling with some new questions. And so in the next step, right, that is the investigation routine. So they start to answer that question. Is there carbon dioxide in the air coming out of our lungs? That's probably something a lot of our students might know, but they only know it because they've heard it before. Maybe they've heard that we breathe in oxygen and breathe out carbon dioxide. And so in the very next lesson, they do an investigation where they gather evidence to prove that, right? Can we prove that a similar reaction to what we saw when we were burning something is happening in us? So they do two different investigations in this unit. The pictures at the top are of them using a straw to blow onto bromothymol blue, which is an indicator which shows when there's carbon dioxide. And then they also do some more in-depth data collection using a carbon dioxide sensor to get some graphable data in that investigation. These are some screenshots of some images from the slides and from student notes. They collect data through those two investigations, and they spend some time discussing what they found out and sharing their ideas as a class to start to build some science ideas. We're going to skip over this video, but like we mentioned previously, you can always go back to the slides and watch more of them or watch this one. But this is a clip of students discussing those different questions. Okay. So after the investigation, we've gathered some data. We have all these different things we've tried out. The next routine is the putting the pieces together routine. This is routine 4, and we're thinking about the question, how do we help students put science ideas together? So we've collected all this evidence. We have all of these questions. How do we start to gather these answers and make sense of these big ideas? And so we're back to the plate tectonics unit. We'll just look at an example of the putting the pieces together routine from that unit. So that was our Mount Everest earthquake phenomenon we experienced. So in lesson 7, it is a putting the pieces together lesson, and it starts with students taking stock of everything they've learned and figured out so far from lessons 2 through 6. So what evidence have we collected so far? What investigations have we done? What types of things have we made sense of so far? And this is in the context of modeling. So they list these ideas, they work as a individually, they work with a partner, and then they come together as a class to list the things that they know at this point, right? We're 6 lessons in that we've figured out are going on and can help explain the phenomenon. And students create models in small groups. They do a gallery walk where they look at different groups' models. And our models now are very different from those initial models that we developed at the beginning, right? Not only because individually we figured things out, but we're also working collaboratively with our group and looking at different ideas they have through this kind of gallery walk thing that they're doing in this bottom picture. And then the last part of this putting the pieces together lesson is we come back to that driving question board. So we go back to those questions we had at the beginning and we see if we can answer them. So this kind of series of pictures shows how this class chose to do it just logistically. So their questions from their driving question board up here. students went up and found a Post-it with a question that they could now answer. They took that question off and then they put it on this little piece of paper. The question is right there, and then they're writing their answer next to the Post-it, right? So all of these pieces of construction paper represent a question with an answer, right? So now we have all these answered questions on our driving question board compared to, we have a few still left over here at this point in the unit. So we're going to take stock of, we don't have a ton of time left, but we're going to take stock of an example driving question board. Okay. So on this slide, you'll see the lesson question for lessons 2 through 6. Okay. So the focus for lesson 2 is how are earthquakes related to where mountains are located? 3, how does what we find on and below Earth's surface compare in different places? 4, what's happening to Earth's surface and the material below it during an earthquake? 5, we're getting into plate movement and how that affects the land around mountains. And 6, how could plate movement help us explain how Mount Everest and other locations are changing? So on our Jamboard, if we look at slides, they're all the same, but slides 4 through 9. So let's all maybe jump on slide or frame 4. We'll see examples of student questions. So these are real student questions that came from some driving question boards. And down here, we'll see some stickers with numbers 2, 3, 4, 5, 6. Each of these numbers represents one of the lessons that at this point in the unit we would have covered. Okay. So your task is to look at these questions and compare them to our student questions. And if there is a lesson question that seems related to something a student asked, one of our Post-its, you're going to drag that number to that sticky. Okay. Maybe partially related. So for an example, lesson 5, how does plate movement affect the land around mountains such as Mount Everest? Okay, that would seem related to this question. How many plates are under Mount Everest, right? That is similar. Okay, so go ahead and take a minute to compare these questions for lessons 2 through 6 to student questions, and feel free to drag those stickies, these little numbered stickers, to Post-its that connect. Okay, we're going to keep moving for sake of time. Right, but if we look at our example driving question board, right, there are some that we've answered, but then there are quite a few that are still unanswered, right? And we're about halfway through the unit in this example, and that leads us into the problematizing routine. So this is our last routine out of the 5, right? And units go kind of between and from one routine to another, but this is the routine that organically comes after what we just did after analyzing our driving question board, right? Problematizing, how do we push students to go deeper, right? We just saw all of these questions we've now begun to answer, but then there are quite a few that we haven't yet. And so problematizing is thinking, where do we go next? We've figured out X, but now how do we figure out Y, right? So evaluating what we know and what we still don't know. And so an example of what this looks like from back to the McKenna unit to 7.3 is sometimes the problematizing routine looks like foregrounding a new question or a phenomenon, right? So helping direct students into something that we haven't figured out yet. So in this example, they look back to some of the symptoms they'd seen previously, and they realize that we can explain some, but not all, right? And this begins to lead them into this idea that how can something that's happening in McKenna's digestive system impact the other systems in her body, right? So we figured out what's going on in her digestive system in this point in the unit where this lesson comes in, but there's all these other things we still don't know. And then that segues into the rest of the unit. Okay, so we've seen all 5 of these questions and how we respond to them through the different routines. And over the course of the unit, like we mentioned, every unit starts with that anchoring phenomenon routine, and then we move through those other 4 and kind of go back and forth between them throughout the rest of the storyline. And all of this is to support coherence from the student's perspective. Do they really feel ownership over their learning? Do they really understand how their learning has progressed? Are they able to make those connections? And so just a quick quote on here that came from a student. I'm really excited for this unit because I feel like last time in my last unit, we had a whole bunch of crazy ideas. And then at the end, we pretty much made all of them happen. So I'm excited to see what we do for this unit, right? I think that really speaks to the student feeling like they owned what was happening in their classroom and that they had control over what they learned and how they learned it. And that's it. And we thank you for joining us today. Matt and I are very grateful to have the opportunity to speak with you this afternoon. On the next slide, you'll see a bunch of links. So if you're interested in learning more about OpenSciEd specifically, there are a bunch of links on there that you can access to give you some more info. You could go and download our materials or view them in the Google Drive today. And if you have any other questions, we have about 3 minutes. So you can unmute or you can drop them in the chat and I'd be happy to answer them.
And I dropped a chunk of those links in the chat, and some additional ones to get you straight to the units that we talked about in the presentation today and sort of the storylines for those units. There's links to webinars for about each one of the units. There's Facebook groups set up for all of the units so the teachers that are teaching them interact around, and then put in links to, if you're interested in doing more than just a little snippet, really to get into the professional learning to support these sorts of transitions in your classroom. There's a link there to sign up for an online PL event. They're not free. We make the materials free. We cannot make our professional learning free. Or you can request professional learning for your district on there. I should also note that OpenSciEd's materials are in the loop in the process and being reviewed at the state level in Nevada. So hopefully that will roll out when those reviews are done. We're also being reviewed by Ed Reports, and that should be out early next year. So thank you, everybody.